Good morning, students. We're going to finish the notes on section 5.6, harmonic motion. We started them the other day. I did email you the notes outline, and this is what we already had compiled the other day, but I'm putting it all in one place. So these are the three different forms of harmonic, simple harmonic motion. I've got the sine function forms, and the cosine forms would be exactly the same. You just replace with cosine. Notice that period is 2 pi over omega, and that would give us time per cycle. Frequency is omega over 2 pi, which is also called V, and that would be cycles per time. Omega is angular velocity, which is the change in angle over time. And notice that period and frequency are reciprocals of each other. So we would reference or use the form of the function that best matches the information that we're given. And then this one would have vertical and horizontal translations. So we have those. Now we're going to dive in with this example. So we've got a cork floating in a lake, and it's bobbing up and down in simple harmonic motion on the waves made by the ripple. So the displacement above the bottom of the lake is modeled by this function where y is measured in meters, and they're going to be the height above the bottom of the lake, and t is time measured in minutes. So the first thing is we want to find the frequency. So frequency is equal to omega over 2 pi. So omega, this is A cosine omega t plus 8. So frequency is exactly 20 pi. Now, if we're going to sketch this, we should probably gather some other information from this function. Well, let me back up and remind you that frequency, I didn't finish it either, over 2 pi, it equals 10. And frequency, as we just looked at, the units are cycles per time. So this would be cycles per, and our time is measured in minutes. So I'll call this bobs because it's bobbing up and down, bobs per minute. So that's what frequency represents. All right, so let's look at the 0.2. So that's going to be amplitude. So amplitude is going to be 0.2. So that means it goes up 0.2 above the surface of the pond or lake, and down 0.2 below the surface of the pond or lake. And then this plus 8, that would be our D value, or wait, I was using K, HK, sorry, it's K. So 8 is the vertical shift. So the middle, horizontally, sorry, vertically, is at 8. So the surface of the lake is at 8 meters. So let's see what we've got here. I think we have enough information to graph it. Although actually I do want to talk about the period. So if we calculated the period is reciprocal of frequency. So 220, no, I started it right. 2 pi over omega. So that's 2 pi over 20 pi. So the period is equal to 0.1. That would mean it's 0.1 minutes per completed cycle. All right, I'm going to graph. Super rough sketch. And I've got a little break in my vertical axis here because my middle is at a height of 8 meters. And it only goes up 0.2. So the highest it goes is to 8.2, and it only goes down 0.2. So the lowest it goes is 7.8 meters. So if I start graphing this, I've got a cosine wave. So that starts at a peak, and it's going to make its nice cosine wave, and it goes down to a minimum of 7.8 and back up to a peak. And then it keeps repeating, trying to make these nice and uniform. And it keeps going on like this forever. So we know that the period is 0.1. So it finishes one complete cycle in 0.1 minutes, 1/10 of a minute. So it gets back to its starting point here. So that would take 0.1 of a minute. And then it finishes another cycle here. So that would be at 0.2. Then it finishes another one here, and that would be, that's 2. And that would be at 0.3. So that's what that function looks like. Now, we already answered this question, but what is the maximum displacement of the cork above the bottom of the lake? And the highest that it goes is 8.2, and the units are meters. Right, moving on to the next problem. We have a 110 volt alternating electrical current, and the voltage varies between positive 150 volts to negative 155 volts. And we have a frequency, so we've got that of 60 hertz, which is cycles per second. And we want to find an equation. So let's start with, what does this 155 to negative 155 represent? So peaks and valleys. So that's related to amplitude. And since this is symmetrically above and below 0, I can safely say that my amplitude is 155. I do have to decide if I'm using a sine or a cosine. And with lack of other detail about whether it starts at a peak or a middle, I can choose whichever one I like. So I'm going to, for no special reason, decide that I'm using cosine. So what that means is that at t equals 0, so I start, the function evaluated at 0 is going to be at a peak, and I know that my peak is 155. All right, so I've chosen cosine. And now I have frequency, and remember it's 60 because that was given. Frequency is V in the function. So I'm going to use my form where I have V in it. So that would be amplitude, which we decided is 155. We're using a cosine function. 2 pi V, so 2 pi times V, which we know is 60. And there's a T. So that's it, but let's combine these coefficients. So f of t equals 155 cosine, 2 times 60 is 120 pi times t. So super rough sketch just to get an image of what this looks like. So a maximum of 155 centered at 0, minimum of negative 155. I've got a cosine function, so I start at a peak, and it's going to cycle up and down in a nice uniform way as cosine waves do, and it'll keep going forever, and that's what it looks like. Great. All right, next problem. Now we're moving on to another concept, which is damped harmonic motion. So it's related to simple harmonic motion, but it's got a twist or complication. So imagine a spring attached to the ceiling, hanging down, and you've got a weight attached to the bottom. If you pulled that weight down and let go, it would go up and down and up and down and up and down. And that's what we've been doing with simple harmonic motion. But if you actually let go of this weight and there's no motor driving it, it doesn't go forever. It's going to eventually stop moving up and down. So what would happen if you let it go is it would slow down on its up and downs. So they would get shorter and shorter, if you will, until eventually it stopped going up and down. So that is what damped harmonic motion looks like. So the function that represents this is k e to the negative ct sine or cosine omega t. So the corresponding cosine function is k e to the negative ct cosine omega t. So c is going to be the damping constant. And k is the initial amplitude. And then these facts are the same as they have been all along. Omega over 2 pi is frequency, again, which is cycles per time. And the reciprocal 2 pi over omega is equal to period. And that would be time per completed cycle. Okay. Reminder, that's the same. So we're going to do a couple of examples. So we have two different spring mass systems. So just like my little graph here, and they have damped harmonic motion. So this is a typo. That should not be 0/5. That should be 0.5. And cycles per second, so cycles per time. So we know that's frequency. So V, which is frequency. All righty, so that's helpful. So we know that fact. And they both have an initial maximum displacement of 10 centimeters. So 10 is equal to the initial displacement. So that's my K value. And then they have different damping constants. So those are written again here. So the damping constant for my first spring system is 0.5. So that's my C. And the damping constant for my second one is 0.1. So that's my C for this one. So I'm ready to write my cosine function for this situation. So I have y equals K, which is 10, e to the negative C, which is 0.5 times T, cosine of 2 pi times the frequency, which I know is 0.5 T. These happen to be the same number, but they weren't from the same place, right? I had a 0.5 frequency, and then here I had a 0.5 damping constant. So I'm going to simplify this a little bit, and I have 10 e to the negative 0.5 T cosine 2 times 0.5 is 1, so pi T. Now I'm going to write this one. So I know that everything is the same except the damping constant. So I'm going to just replace the damping constant with the 0.1. So this would be y equals 10 e to the negative 0.1 T cosine pi T, and that's my other function. So I do want to draw a little rough sketch here, but let's look at it on a graphing tool. So let's look at this graph in Desmos and see what it looks like. So if you look at this graph in Desmos, the red function is my damping constant of 0.5. So notice that it starts off big and it very soon levels out until just after 10 seconds, it's not moving up and down at all. And compare that to my damping constant of 0.1. So the blue function starts off with a big amplitude. And it doesn't slow down super fast. I've still got waves going on way out here until like 45 seconds or later. So it takes much longer to be damped or slow down. So my bigger damping constant of 0.5, the red one, it slowed down very soon. And my smaller damping constant slowed down eventually, but not as fast. So the size of the damping constant affects how soon it slows down with its up and down motion. So back to our notes. If I make a rough sketch just to have them in my notes. This one started off big and slowed down pretty soon. And this one with the smaller damping constant started out big, had the same frequency, but it kept going way, way out before it started slowing down. It's actually even more dramatic than I drew. So the bigger damping constant flattens the curve sooner. Right. One last problem. So last page. A stone is dropped in a calm lake causing ripples, meaning little waves. The ripple effect is modeled by damped harmonic motion. At some time, the amplitude of the ripples was measured, and then 20 seconds later, it was measured again and found it had dropped to 1/10 of the original value. And we're just trying to find the damping constant. So it doesn't actually matter as far as the damping constant, whether we have sine or cosine, and we have no other information, so we can pick one. So I'm going to use a sine representation. So this is the form, right? And I'm interested in amplitude. The only information I have is about amplitude. So if I had a simple harmonic motion, it would look like this. And the only thing that affects amplitude is this coefficient here, omega t, that does not affect amplitude. So this is the only information that affects amplitude. So I'm comparing this whole coefficient here, that includes CT, CK, yeah. So at time t, sometime the amplitude is measured. So the amplitude would be this part of the expression, K e to the negative CT. And then it's measured again 20 seconds later. So at time, this one, plus 20 seconds more, it's measured again. So the amplitude at that time would just mean that I'd put t plus 20 into the t position. So that would be K e to the negative C times t plus 20. And how do those compare? So my situation said that 20 seconds later it was measured. So I'm writing that down. This is the 20 seconds later time. And it turned out that that was 1/10 of the amplitude that was measured at that first time t. So 1/10 of that, K e to the negative CT. So now I have an equation I can solve. So the first thing I notice is I have a multiple of K in both sides of the equation. So divide by K. So now K is gone, and that's nice. And I'm just going to have C's in here. E to the negative CT plus 20 is equal to 1/10 e to the negative CT. I'm going to distribute the negative C through here. E to the negative CT minus C times, oops, actually C times 20, but I'm going to put the 20 in front. Equals 1/10 e to the negative CT. Now, quick reminder over here, properties of exponents. If I have a base raised to an exponent times the same base raised to an exponent, I can combine those with the same base by adding the exponents. I can use this property in reverse. So if I have a base and I have a sum in the exponents, I can split it into a product with the same base with those exponents that were in the sum. So I could split this into a product of e to the negative CT times e to the negative 20C. And I didn't do anything to the right-hand side. So notice now I have a common factor on both sides. So I can divide both sides by e to the negative CT, which is really nice. And now I'm left with e to the negative 20C is equal to 1/10. So this looks like a natural log problem to me. Natural log of e to the negative 20C is equal to natural log of 1/10. So bring the coefficient in front. Natural log of e is 1. I'm going to leave this alone over here on the right. Last step, divide by negative 20. So C is equal to the natural log of 1/10, all divided by negative 20. And if you evaluate that on your calculator, it turns out to be 0.12. And the entire goal of this problem was to find the damping constant, and there it is. So we're done with this problem.